Okay. So today I'm not really planning to use the Blackboard unless there's something we want to uncover. So I'm going to be talking about kind of how we're scaling up this trapped ion architecture and the kind of leading ways that folks are doing that. And then I'll tell you about the systems that we're running at Duke in particular. And then the second half of this will be more of like a research talk on our latest experiment having to do with measurement-induced phase transitions. So I know y'all learned a lot about that earlier in the school, so I'll cover that in the second part. Okay, so first, a little bit of scaling. So the first ion trap architecture I'll talk about is what we call quantum CCD, QCCD architecture. And the idea with this is that you always keep your chains of ions very small. In fact, exactly 2 ions at a time. And then you're constantly moving those ions around. And rearranging them to do different combinations of gates. So here's just an example. So let's say I have these 4 qubits, 0, 1, 2, 3. So, and I'm trying to execute this circuit. So in the first layer, I need 2 qubit gates between 0, 1 and 2, 3. So they're trapped together, each in so we have 2 ions in this well and 2 ions in this well. And then I physically transport ion 0 and 3 out of the way in order to do these single qubit gates on 1 and 2. So now 0 and 3 they're not seeing that laser light at all. So there's no crosstalk. We can move them far enough away. And then the next gates that we require are 0, 2 and 1, 3. So in this architecture where they're on this linear line, we can actually physically swap them in space vertically. So that's what this transport represents. So now they're in a different order. We have 0, 2, 1, 3, and we do those final gates in these 2 zones. So this is just a little example of how the QCCD architecture would work. And so this is just 4 qubits, but this is extendable, has been extended to up to 32. And so the best example of that right now, I think, is from Continuum, which is right down the street here in Broomfield. And so they started with this linear trap that I was just describing, where you can still swap ions in space, but everything's moving on a line. And then their latest trap that they've released is this racetrack, where you just take this linear one and curve it around to make a circle. Okay. And so now not only can you move them in the linear fashion, but you can also turn the corners and rearrange them that way. So this provides a little bit more efficiency in the ion rearrangement if I need to get a gate between the 2 that are furthest apart from each other, right? And so the idea with this is that you can continue to extend this to something like a 2D grid. And I'm remiss, I don't think I have a junction picture, maybe later, but we know how to move ions through little junctions like this, where we have 2 lines that are meeting. So we're not restricted to kind of making lines and circles. We can make a grid. And so now you can move your qubits around in this sort of grid, like cars in a city. And then the next step, so I told you how we do our gates. We shine lasers on the ions. You can already see, once you start arranging them in a 2D grid like this, and you try and shoot laser beams from the side, you're going to be hitting ions you didn't intend to hit, right? So as it gets more and more dense, we actually need to deliver the light from the chip itself. So that's what this is talking about, integrated optics. The idea with that is the ion is trapped here above the surface of the chip, and you send in a photonic waveguide that ends in some kind of coupler that sends the light up onto the ion. And so everything happens like within the chip. And so now we don't have to worry about sending lasers across the chip. We can make kind of arbitrary layouts on the surface. And then they have ideas about how to link these kind of grids together. So this is one approach to how you can scale up with ions. It does include a lot of transport, a lot of shuttling ions around. And in some sense, right, the internal energy level of the atom doesn't care that you're transporting things around. This is not a problem. You can move it all around this trap and keep your qubit. It doesn't affect our T1 or T2. It does affect the motion, but in this architecture, you just recool the motion before every gate. So you're always returning to the ground state before every gate, and you keep high fidelities no matter how much transport you've done. But of course, there is a cost, and that is in time. So you can only go so fast before you kick the ion out of the trap, or create collisions that could create motional states that you can't even cool. Or so in the slowest limit, you do this adiabatically, right? You just kind of move the well slowly across the chip. There are ways you can also kind of kick it and then stop it, just like you would, I don't know, think about like classically moving these ions around. There's nothing quantum about this transport. It does take a lot of time. So there's a lot of overhead with that. So the other architecture is what I'll call like the long chain architecture. So this is, oh, there we go. So this is an example from IonQ. So they have their chip here, and it's just a linear chip. And instead of trapping many small chains, they trap a single long chain. And they do the gates exactly how we talked about last time. So you can choose any pair within the chain. And what's great about this is it's kind of like it's random access, right? You don't have to rearrange the ions to do a particular gate. You just turn on those laser beams. So the ions are stationary in space. So we don't have this overhead of shuttling ions around. But there is a limit to how many ions you can put in a single well. And it has to do with the fact that the more ions you pack in, right, the more you have to relax the trap in order to fit them in without them like buckling into something that's not a linear chain. And so that kind of sets the limit on how many you can put in a single chain. And there's lots of like technical things I could go into on what that number is, but in this IonQ machine, they have 32 qubits in a chain. And then for the Raman beam, so this is a ytterbium system. They have 32 Raman beams on either side that are intersecting on the ions in the middle. In our systems that do examples, we have one system where these beams are going actually through a hole in the trap. And then we use one big global beam that hits all the ions for that second Raman beam. But just by having these individually focused beams on each ion, we can do all qubit gates, and we can do sort of any pair of 2 qubit gate that you want. Yes, questions?
If you had multiple of these platforms where you have all connections within a single chain, is there a way to interact them?
Yeah. So good question. So what would you do next? So the idea that IonQ is going with next is taking these long chains and then hooking up with photons. So I didn't talk about this, but you can create ion photon entanglement and then collect those photons and send them to another ion, and thereby, or rather send them to an interferometer and do this with 2 ions and create ion-ion entanglement. And so this is something that's been an active area of work in ion trapping. And so if you can link up these long chains with photons at a high enough speed, then you could create kind of this like multi-core processor. I think the current record of ion-ion remote entanglement is 180 hertz. So that's where the link up time overhead comes in with this architecture. So either you're moving ions around a lot or you're waiting on photons. So you kind of have to see which architecture ends up engineering this problem away first. Okay. Any questions on the kind of big picture of how we would scale this? Yeah. So right now, shuttling is more efficient. But it's unclear like when you want 100 or 1,000 qubits, whether you can be shuttling 1,000 qubits around all the time. So then maybe photonic links become more important, but the like current record rates are just so low. And I think a lot of that is, it's just all engineering. There's nothing like physically limiting those entanglement rates. So yeah, we just have to see. Back. Good question. Okay, so currently in the long chain architecture, everyone's doing their gates sequentially, not in parallel. You can do them in parallel, but the fidelity is lower than doing them sequentially. So we have these long coherence times. So when you're in the long chain, like time is not free, but it's freer than the costs you take for doing parallel gates. It's lower costs. But there are also some schemes that have been shown recently for doing parallel gates and long chains that are seem to be higher fidelity. So I think that's still kind of open. And then what was the first half of your question? Oh, 2 qubit gate fidelities. Yeah. So in the 2 ion case, right, I think Continuum is consistently hitting close to 3 nines. But in the long chains, I think more like 99.5 is kind of the best on average. That's in the 32 qubit chains. Okay, so now I'm just going to talk about some of the systems that we have at Duke. I know a lot of you are theorists, and we work with a lot of theorists, and we try and see what we can do with our quantum computing systems that we have available to us. So I wanted to give you a picture of what those look like in practice in an academic lab. So I've made references to like Quantinuum and IonQ, which of course are companies, but these are systems that are being run at a university. And so the workhorse ion that we have at Duke has been ytterbium-171, which we talked about in the first lecture. And so I won't repeat too much of that. And we use this ground state hyperfine qubit with a qubit splitting of 12.6 gigahertz. And then I think I flashed this data before, but this is a T2 measurement in our system that we have at Duke on this spin with about 4 seconds of microwave coherence. And this is in a chain of 15 ions. So this is something that it doesn't matter whether we have 1 or 15, we still get good T2s. We are trapping with a single long chain architecture. And so this is an image of our ytterbium-171 chain, and it's equally spaced in the middle here, which I'll talk about why that's important. And we do that using these ion traps that are made by Sandia National Laboratories. So we have a great partnership with them, kind of, and they do this nationally for lots of different groups where they've developed methods to make these chips that are reliable and that provide the amount of control that we need in order to make these long chains happy. So I talked before about how we do this detection. So we have our spin state, our qubit state down here, and we shine in this 369 nanometer light and look for photons. And so if we see no photons, then we know we were in 0. And if we collect some, then we know we're in 1. And in this system, we actually threshold on 1 photon. So either we see 0 or we see 1 photon, and that is enough to tell us the state of the qubit. And we do that using, it's a little difficult to see the scale, but this is an array of fiber cores. So it's like a bunch of little fiber cores lined up next to each other. And what we do is we image the chain onto those fiber cores so that each ion has its own fiber for collecting the light and sending it to a detector. And so these are equally spaced. So this is one reason it's nice to have an equally spaced chain. And by doing this and each having their own detector, we don't have any detector crosstalk, and we can do this alignment very well so that our detection fidelity is over 99%. In this? Yeah, so this was probably taken for like a pretty long time, just to show like an example of a histogram. And so, yeah, so yeah. So you turn on this light for some amount of time and just collect how many photons, and then you could do, I think in this example, you prepare like 0 plus 1 and then do this like 100 times, and then you plot all of the instances of each number of photons. Okay. And then our laser qubit operations are done with this UV laser, and we have a 2-photon Raman process, which I've mentioned a couple of times. And in this system and a couple of others I'll talk about, we have individual beams that are focused on each ion. And that allows us frequency, phase, and amplitude control of this, basically this qubit laser for each ion. And then with a second beam that hits the entire chain at once, we can do all of our Raman operations. But because it's a 2-photon transition, we hit an ion with that global beam. If it doesn't have its individual beam on, nothing will happen. There's no gate. So this is how we get away without having to do individual beams from like 2 sides. So 1 global and 32 individual is enough. Okay, and we use these MS gates that I talked about, which give us this Ising gate here with a variable angle. And in this particular example, we use amplitude modulation. So our XX gate is split into all of these different discrete time steps, and then we modulate the amplitude of the laser in order to create entanglement and return to the origin in phase space. So, and this is how long our gates take. With about 15 ions, it's about 200 microseconds. Okay. And we can couple any pair in the chain. So we're usually working with a chain of 15, and we use the middle 13, for example, and we can have 13 any pair gate between them. Okay, putting that all together, this is kind of a shot of what we call the blue system looks like. So this, these are, let's see, officially fidelities and spam and everything from before we moved the system from Maryland to Duke. So this was previously at University of Maryland and has since in the last couple of years moved down to Duke. And we are just about back to these fidelities from before. So we can get, now we're working typically with more like 20 qubits. So we've got slightly longer chains and working towards this similar 2-qubit gate fidelity. Our single qubit gate fidelity is usually very high. We can do kind of some pulse sequences to make those as 99.9 is plenty for us, considering it's much better than our 2-qubit gate. And then, as I've mentioned, right, like our measurement errors are really small. So our spam error is about 0.5%. Okay, so that's the blue system. And we've also added some new capabilities into this one. So another thing you can do that is common in ions is called sympathetic cooling. So the idea here is you take another species or another isotope of ion that has spectral lines that are well separated enough from your qubit. So you can talk to that other ion and cool it without affecting the information in your qubit. And so the way that works is we have this transition here up to the D3 halves from the ground state. So in ytterbium, this is 435. And this is a narrow transition. And so we can selectively turn it on for 172s. So we trap our chain, put some 172s and some 171s together. So the 171 is our qubit, and that has the Raman lasers. But then we also send in this 435 light that can talk to this 172. And we can use that to essentially do Doppler cooling or sideband cooling without affecting the internal state of the 171. So this is commonly done with ytterbium and barium, for example. And then in this case, we're using 2 different isotopes instead of 2 different atoms. So that's something that has been kind of in the works, adding to the blue system. The other thing that we've been doing is mid-circuit measurement. And so in the QCCD architecture, yeah. How do we control it? So we load the chain like 1 atom at a time. And we can use the laser, like we load using photoionization. And so we can tune the laser and choose which isotope to load at which time. So that's true as long as that photoionization line is also narrow enough and has enough spacing between the 2 isotopes, which in the case of ytterbium it is. So we can do this isotope selective loading and just kind of load the chain in the order that we want. Good question. Okay, so we do our measurement by shining in a laser. And so if you have qubits that you don't intend to measure that get hit with that light, then you'll have an error, right? And so in the QCCD architecture, they're just moving these single ions around. So they can always just move them out of the way and do a measurement. In the long chain, what we do is very similar. So we take the long chain where we're doing our gates and all of that. We can split it into pieces that are shorter, say like half and half, and then measure in one region while we keep the rest of the chain in the other. And then we can put them back together and start all over again. So this is a video. So this is like a real-time video of how we can take the ions. We split it into 2 chains here. And then in this example, we actually do a second split. So we bring these back to center. And I believe there are 8. And then we split them into 3 and 5. Yes.
Can you remind me of this chain? Are you able to reorder the ions to measure their subsets?
Yeah, so it's a little trickier because you can only kind of swap 2 ions at once. And so actually this double split is exactly what we would do in order to do that. So you split it once, you split it twice, and you leave 2 ions in the middle, swap them, put it back together, and start again. And so we've demonstrated, not like published yet, but we've been demonstrating this kind of reordering process where you take some arbitrary order in the chain and then sort it to be the order that you want. Because we do have collisions that can reorder the chain. Okay. And so we use this in a verification project that you can check out that has some of the technical details, but this is something that I would say we're still kind of adding to our toolbox. Okay, so that was more about our kind of old system. We have a new one coming online. They're doing the first 2 qubit gates right now back in the lab. And it's very similar to our first system, but kind of has little upgrades on every little aspect, things that we learned in building the first one that we were able to correct in the second. And so it still has individual addressing, and it's a long chain of ytterbium qubits and built similarly for up to 32. We made some big changes. So for example, you can see like this is a chamber where we actually have the trap. This is like CAD model, but this is like the picture of it in person, which is not quite as pretty. And surrounding the chamber are these black boxes, which contain all of the Raman optics. And so all of the Raman optics are enclosed with nitrogen purging, which keeps things very clean. UV light is not kind to optics when they're dirty. And this should also keep away any kind of air turbulence, keep things thermally stable, which all helps with improving our T2s, our laser phase coherence. And so we're looking forward to seeing what we can do with this system. The other thing that's going to be new in this is we're adding in yet another laser. So this is another transition to this F state in ytterbium. So this is another weird thing about ytterbium is it has this F state up here. And we can address that with 411 nanometers. And it's a narrow transition. And so we can use this to basically hide the qubit up in the F state. If we wanted to do some kind of readout where we were addressing all the ions, you could hide your qubit state up here for the qubits that you want to. And so there are some schemes that we're exploring on how to use that for readout, but then also there's, of course, this is an F7 halves, so there's many different levels up here as well. And so we can also make qubits in that F states or qubits. So having this 411 added to our capabilities kind of adds some new possibilities there. And so in this system, we similarly have our individual beams here and then a big global beam that hits the whole chain. And in Raman, you want a big delta K that determines the momentum kick that you get. And so this is kind of maximally giving us the best delta K you can get. And then this is a picture of what our individual Raman beams look like. They're actually elliptical. So they're narrower along the chain of the ions, which reduces the crosstalk from one ion to the next. And let's see. Yeah, so with this system, we also have really taken to heart this kind of systems level control philosophy. So we're not putting this on the cloud by any means. We're never going to have the sort of interface that you would get from a company and typing in your circuits on the cloud. But we are able to engineer a lot of passive stability as well as controlling all of the different components happily together. So I think I'm actually gonna, yeah, okay. And then I'll mention just kind of briefly what we're planning to do next. So we're building what we're calling the green system. And this is gonna be using barium qubits, either 133 or 137, depending how things go. What's cool about barium is there's no more UV light. So instead of the 355 Raman, we're gonna be using this 532 nanometer light for the Raman transitions. Other than that, 133 looks a lot like 171. It's a nuclear spin 1/2, so we have a similar hyperfine structure. And then we have this nice narrow D5 halves, so we can do these kind of shelving or have qubits up here. And it's IR laser. And then the readout is 493. So we've gotten rid of the UV, but kept all of the nice atomic properties. Of course, there's always one thing, right? So the one thing about 133 is it is radioactive. And so just a small thing. But there's ideas of how you can make sources that are small enough where the radioactivity is perfectly safe and below any kind of background levels, because we don't need that many atoms. So the other option is to use 137, which is spin 3 halves. So there's slightly more levels to deal with, but it's totally doable. And in this system, we're using still like this linear trap from Sandia National Laboratories, but instead of a single long chain, we're aiming for 4 long chains, where each of these chains has laser beams, just like before, individual beams for each ion in each zone. So instead of 32, we would have 128 possible qubit locations. And then we can do basically taking that shuttling sequence I talked about, where we can split these long chains and move them around to the next level, where we can do it between these 4 zones. So the strategy here is somewhere between the QCCD and the long chain to kind of combine our experiences with the long chain, but gain some of this kind of rearrangement you get with QCCD. So this is something we are designing right now. So this is kind of what we think it's going to look like. It's going to be housed in a cryostat. And again, we have our black boxes for the Raman system. And then you'll notice there's actually fibers here as well. So what's great about 532 is you can put it in a fiber. So yeah, so we're excited about this. Okay, so are there any other questions on kind of architecture and scaling and ion hardware? Yeah.
I wasn't clear in the where you were showing the little square arrays. Are they arrays of 1D things and can only do owner and get assisted gates like in one line, or do them?
So in this picture, this is like a snapshot, like 1, 2, 3, 4 snapshots in time.
Yeah, I meant earlier where you.
Oh. Oh, and it's in like a grid. Yeah. So the grid is, I think of it as kind of like it's like the streets in the city, but you still have to like bring the two ions together to do a gate. And so you would have certain zones that are indicated as like, okay, this is a gate zone. And I would take the ions there and do their gate and then take them wherever they need to go. Yeah. Okay. So I think before I dive into the next topic, because it's going to be completely different, let's just take a few minute break and then we'll come back in just like 3 minutes. Okay. Just gonna sit down for a minute. I'm gonna run to the bathroom. Let's do this out for a second. You can help me get it back on. Just a good. Okay. All right, we're gonna get started. Yeah.
Oh, sorry.
Okay. I think pretty much everyone's back. So let's jump in. Okay. So first I'm gonna start with a little tutorial on magic. This is something that I had to learn myself working on this project. So I'm by no means an expert, but I'll do my best to explain to you what I mean by that. And then I'll talk about what's presented in this paper that's on the archive, where we both find numerically and in theory, we find this phase transition in magic, and then we show it in an experiment also. Okay. In this particular experiment, we actually ran on IonQ hardware. So this was about the time we were moving from Maryland to Duke. So the timing worked out to use this partnership through the Q Lab at University of Maryland that they have with IonQ so that we can get access to the ARIA machine. And so we have a team here that's a combination of folks from Maryland, IonQ, and Duke working on this project with me. Okay, so I want to start talking about magic by first just sort of talking about the power of quantum computing, right? So you might see, in popular press or people trying to explain the power of quantum computing, they say, oh, superposition. We can be in two places at once. We can create a superposition of all possible inputs to our algorithm and then run it all in parallel. Isn't that great? We can do parallel computing, right? But of course, we know that that's not really it because you still have to measure at the end and you only get one answer every time. Okay, so that's not the power of quantum computing. So then what about entanglement? We know entanglement's important. We know making highly entangled states is hard and studying entangled systems is hard. We also know that the most entangled state you can create, GHZ states, are easily simulated and actually like spoofable, right? So there's something missing here. We can take even combinations of superposition and entanglement, and I'll get more into that, and that's still not enough. So what's missing? What's missing, I would say, is magic. And the more technical word for magic is non-stabilizerness. So I'll talk about what I mean by that. But magic is coming up in more and more places recently. So there's a whole resource theory that's been developed recently about magic, how we measure it, how you quantify it. There's connections to complexity theory, as well as ADS-CFT, the role of magic in holography, as well as it's been proven that magic is necessary for chaos. So it's obviously an important part of quantum computing, but it's something that maybe we don't talk about as often. And today I'm going to be talking about magic in the context of a measurement-induced phase transition. So I'll just review very briefly what I mean by that. So in this kind of popular example of such a transition, right, we have our qubits here in space, and time is going vertically in this picture. And at each time step, you either are doing your random Clifford entangling gates, or with some probability, you measure each qubit. And then you can change this probability of measurement in each time step. And depending on that measurement rate, you get either, if you have lots of measurements, you end up in an area law entangled state. Whereas if your measurement rate is low, then you can keep volume law entanglement. Another way of looking at this is in this volume law phase, your information is protected, right? And so, we look at this and we say, okay, volume law entanglement, it's protecting information. It's doing something that is somehow like quantum powerful. And it's interesting because we can, say that we have like error correcting codes in this space. So it's useful to study these kinds of transitions and understand the properties of these phases, right? Okay, so then I'm gonna go ahead and put another axis on this. So now I'm plotting as entanglement is growing larger and we have this region that's volume law entanglement, and say that this other axis should be maybe magic. And so if we have, maybe there's some transition that happens that we can study where we have a magical phase and a non-magical phase. And when you combine the high magic and the high entanglement, is this where quantum advantage lies? So we want to try and understand the origin of quantum advantage kind of from these different resource theory perspectives. So what resources do you need to do something that is truly powerful in quantum computation? Yeah.
I guess maybe it depends on how you quantify that, but it's possible to have volume law magic without volume law things.
That's I believe, an open area of research. Yeah, open question. Yeah, how do you like quantify the locality of magic? That's a question. Mm-hmm. Yeah, so you can create a volume, like we know we can kind of make volume law entangled states that have magic. But I would say the open questions are, how do you quantify how much magic, and how do you quantify how non-local the magic is? Right, those are open questions. But yeah, magic can be a property of a single qubit and sort of a state, and we're still figuring out how to quantify it. Okay, so let me be a little more concrete now in defining what I mean by magic. So I'll begin by talking about stabilizer states, since the definition is non-stabilizerness. So we can kind of start by defining what it isn't. So a stabilizer state is generated from a stabilizer circuit, which is made of stabilizer gates. So I've done kind of a circular logic here, but these stabilizer gates are what you know as Clifford gates, right? And so these are the Clifford gates here. We have the Hadamard, the phase, and the C naught, for example. And you can convince yourself with a single qubit that if you say, like, start in 0 and you apply either of these single qubit gates, there are only these 6 states that you can access using these Clifford gates. And so you're only getting access to a restricted part of the Hilbert space. Another way of looking at that is these single qubit stabilizer states are the corners of the block sphere, like the extremum of each axis of the block sphere. And so only by using these stabilizer gates, we get kind of restricted access to the block sphere. And this picture extends into the multi-qubit case as well, kind of a similar intuition. And there's one thing that we know about stabilizer circuits. We know that they're efficiently simulatable classically. This has been proven. So you can simulate these Clifford circuits in polynomial time. You can use Cliffords and make highly entangled states, right? But we can still simulate it classically. And so the question is, what role does non-stabilizerness play in the simulability of a circuit? Okay, so now we want to go away from these stabilizers and into something that has magic. One way you can do that is to add a T gate, which was already mentioned, right? T gate or magic gate. And so that's what this gate looks like here. Another context you might have heard of magic states and magic state distillation protocols for quantum error correction. So you start with a bunch of magic states that are kind of noisy and don't have much magic, and you distill them down into a nice magic state that has the resource that you need in order to do universal fault-tolerant quantum computation, which generally is in a stabilizer code, right? Stabilizer code uses stabilizers, Cliffords, so they can't add magic. So you have to start with a magic resource. So that's what magic state distillation is trying to do, is give you that resource to begin your computation. Unfortunately, creating those this distillation process is resource intensive in other ways. So you need lots of qubits, lots of measurements in order to do this fault tolerantly. So maybe if we can understand more about magic, we can understand a better way to do this type of distillation. And then also mention that magic can kind of be a measure of noise, right? So if I take my hardware and I run a Clifford circuit, or what I think is a Clifford circuit, but at the end I have some magic, then I've not been true to the Clifford circuit that I intended, right? So this is kind of an indication of certain types of noise that you might have. And so this was demonstrated as sort of a technique in this paper here. Any questions about this section before I keep going? Okay, so we're all magicians now. You got it down. Okay, good. Okay, so now I'm going to talk about this phase transition that we study in magic. So when we want to look at a measurement-induced phase transition, we need to start with our model. So this is what the model is that we look at. So we have n qubits. First, we do an encoding step, which is a random Clifford circuit. So it's built up in these layers of random Clifford operations. And then we also have this decoder, which is the inverse of the encoder. And so if you ignore the red squares in the middle at first, all we're doing is encoding and decoding with this random Clifford circuit. And we designate some qubits to be the logical qubits and the rest as the syndrome qubits. So we can measure the syndromes and get some information about the logical state. Now, what we'll do in this model is we'll add a Z rotation, a single qubit Z rotation on each qubit. They're all going to have the same amount of rotation, alpha. And we add that in between the encoding and decoding step. And for an arbitrary alpha, this is not a Clifford. And so it can add magic. And so this decoding process will no longer be perfect. And we can kind of observe and measure the magic that's left in this logical state conditioned on the syndrome outcome. So this is where the idea of a measurement-induced phase transition comes in. We're going to have to look at these syndrome measurements in order to see the phase transition. Okay, but so I said we want to measure magic, we want to observe magic, but how do you do that? And so the first thing is I'll just kind of describe what makes a good measure of magic. And some of this you could probably already think of, right? So it should be 0 for a stabilizer state by definition. It should also be non-increasing under stabilizer circuits. I shouldn't be able to add magic by doing Clifford gates, right? And then the other thing is that it be sub-additive for product states. So if I combine tensor product 2 states together, I can't create magic somehow, okay? Okay, so this is kind of some basic requirements for a good measure of magic. So I'll walk you through one example of a measure of magic that's actually quite intuitive. So that first we'll start with an expansion of a density matrix into the Pauli basis. So we take this matrix, say we just have the state 0. I can write it down as the sum of the identity and the Pauli Z. And we say that this density matrix rho is stabilized by I and Z. So this is kind of the language of how we would talk about this. Yeah.
Magic for like random bond. Like if I hand you a random bond, you track it backwards with Cliffords, get a magic. Sorry, I skipped it off.
Yeah, that's kind of a track it back. I don't know what you mean by.
Could you
Uh-huh.
you just go back for any given.
I mean, I'm still not sure I understand your question, but I think the answer is generically no. But maybe we can talk about it after. Okay, I'm still not sure what you're asking. Okay. Any other questions about measuring magic at this point? Okay. Yes.
So how should I understand the sub-additive pitch instead of just being additive? Should I find that funky, or like for example, for entanglement, the effect of the additive?
So I understand it as, right, so this is like if you measure the magic independently for each state and add it together, it's more than the magic when they're when you just take the combined state. So I think of it as, yeah, you can't like combine states and create magic, but in the same way, you can't like combine states and like create entanglement in that way, right?
Maybe as a simple question, like, is there a simple example where you extract a tensor product of two states that by some should reasonably have more magic than the zero one themselves? That's kind of big. But...
I mean, I guess by this definition, no, but I'm not sure.
Oh, sorry. Less than some. Sorry. Hold on.
There probably is a specific example that I don't know off the top of my head. Okay. So, right. So we're going to take our density matrix and expand it in the poly basis. And then we say that those polys stabilize that state. And so then what we'll do is, so now take the example of 2 qubits in the 0 state. So this state is stabilized by these combination of 2 qubit polys. And if you just draw kind of a histogram of the expectation values when I expand into this poly basis, right, it's concentrated around the polys that stabilize that state. Makes sense, right? So if I can take my state and expand it into polys and I only get certain values, then what I have must be a stabilizer state. Okay, but then what if I see something like this, right? So this is an example of a Haar random state. And now if I expand in the poly basis, I have all kinds of different polys popping up. And it's kind of distributed all over this basis. So you can already just kind of intuit how you could use this distribution over all possible polys as an indication of the amount of magic in a state. So a Haar random state can definitely has magic. It's yeah, as opposed to a stabilizer state, which doesn't. That it's distributed over all possible polys. So in the stabilizer case, it's concentrated over the polys that stabilize the state. So there's only 4 of them for 2 qubits. But in the well, I mean, it's distributed everywhere, sort of randomly. And I'm gonna like explicitly quantify it. This is just to give a picture. Yeah. So let me keep going. Okay. So the quantitative way to describe this is using the second stabilizer Rayleigh entropy. And so this defines the spread of rho when expanded into this basis of poly operators. And so it's written like this. So we have inside, this is a sum over all of the poly strings, all of the possible poly strings. And then we have the 4th moment of this trace where this you take the poly string and the density matrix. And so calculating this spread, of course, requires knowledge of rho in order to calculate this. And so naively, this involves full state tomography. It's also been shown that you can do this with a sort of shadow tomography technique and still get enough information to be pretty confident in this measure. Yeah.
So this is the delocalization.
Yes. So I guess I don't say this explicitly, but this satisfies all of the conditions that I talked about in terms of being a good measure of magic for pure states. I should say that. This only works for pure states. And this is something that you can, like, I recommend like reading the PRL where they if you really want to dig into the proof of how it meets all of these properties of magic, or rather being in good measure. But the intuition is just this picture of how, a stabilizer state has a concentrated distribution on its stabilizers, whereas a magic state has kind of a spread out distribution. It's going to be 0. Yeah, you can like, as an exercise to the homework exercise, yeah, to take that and then exactly calculate the SSRE, and you'll find that it's 0 for. You're giving away the solution. Yeah. 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 Mm-hmm. Mm-hmm. Right. Yeah. So we're choosing, right. So the polybasis is inherently special for stabilizer states. Just by definition, you have to have a basis in which you're defining the stabilizer states. And so that's the basis that we are expanding in. So then when we try and expand something that's not a stabilizer state, and that basis then doesn't work as well. So it's kind of intuitively makes sense. Question?
The idea of that measure is that the endpoints.
Sorry, that there are. Mm-hmm. Yeah.
Then it's 0.
Yeah.
That's 1 over 2n. That's where you get log of.
Mm-hmm.
Yeah, so you have 4 that.
Mm-hmm. Yeah. So it's fun to sit down and take a stabilizer state and calculate this for yourself and convince yourself that this is true and that a stabilizer state has 0 magic. Okay, so now back to our model, right? So we have our n qubits, we encode, maybe we add some magic, and we decode, and then we want to measure the magic in the logical state at the end of this process, conditioned on the syndrome outcome. And so a picture of what this looks like now is we start in all zeros, and then we encode into a stabilizer state, which we can think of as being on this kind of grid of stabilizer states. And then this error term, this RZ that happens, takes you off of that grid of stabilizer states. And then the decoding step, which includes the syndrome measurement, either snaps you back onto a stabilizer state or leaves you in a state with magic. And so this is going to be the process that sort of happens as we run this circuit on our qubits. And it's just like a intuition picture. Yeah. Okay, and here's what we find. So I will explicitly say when I show experimental data as opposed to theory. So this is theory. And okay, so what are we looking at? So on this axis is this error parameter alpha. So that's the rotation on all of the qubits that's happening here in the middle. And then on this axis, we have what's called the code rate. So we're starting with n qubits, and then we're designated k qubits as logical qubits. And so the code rate is the fraction of the qubits that I'm keeping as logical qubits. So if so for example, if the code rate is 1/2, then half of my qubits are logical and half are syndrome. Okay, and what do we see? So the colors are indicating the magic as measured through this second stabilizer ring entropy that I just described. And what you can see, so this line is just kind of to help you guide the eye, where you can see there's this region here that has high magic, and we call this the magical phase. And there's some kind of transition that's happening, which is what we're interested in looking at along this curve here. You can also see, so if you look kind of along this axis, right? So this is increasing that rotation that I do in the middle. So if I do nothing, right, I have no magic. Then if I, do something in between that, maybe I have some magic, but then I return all the way to 0 magic, because when that angle is pi/2, then I'm just doing a Clifford. So I should have 0 magic on this end of the phase diagram, and we see that. And I'll break down kind of different cuts in this phase diagram as we go along. Question? Yeah, exactly. So we'll see that more as we go. Yes.
So I guess the reason why measurement is necessary at the end in a pure state for this particular modifier, or is there another reason why that's
yeah, so we still have to condition on the measurement record in order to quantify this magic, right? So I said that when you do this decoder step and you measure the syndromes, you kind of snap into one of these two states. And so you need to know kind of based on the syndrome, like what happened.
But I guess if you had some sort of mixed state magic.
Yeah, I'm not going to touch that. Yeah. So like the pure state magic measures are pretty well established. But beyond that, it's really not.
Yeah.
It's like a.
I guess I'm just wondering if the measurements are physically important or if they're just necessary to get a pure state.
It doesn't guarantee that I get a pure state. When I do this on a noisy quantum computer, yeah. But I guess yes, in theoretical sense, yeah. Okay, so let's look into this phase diagram. Okay, so first I'll take the case where we have what's called a vanishing rate. So we always keep one logical qubit and just increase n. So as n gets very large, we have the code rate goes to 0. And so in this particular case, so now I vary this alpha parameter. So this is oriented in the same way. So on the right, this is what we call the Clifford point, where this is shifted by pi/2, right? So this is when it's a pi/2 rotation. And what you see is in the inset, right? So as n increases, this peak in the magic gets pushed towards that Clifford point until it would eventually kind of vanish into the Clifford point as the code rate vanishes itself. So in other words, this vanishing code cannot support a magical phase any longer. And then if you scale this by 1/√n, then we see a scaling collapse in the magic. So this is still looking at SSRE in the magic. Yeah. And in this case, right, it's only one logical qubit. And so I can do full state tomography with only 3 measurements, not a problem. So this second stabilizer reigning entropy is something that we can measure. We do a couple of additions to that. So the first one is that it turns out in this post-selection process, there are only kind of it's a single qubit, right? So there are only a certain number of actions that can happen on the logical qubit during this process. But there's many syndromes, but we can group them in terms of what happened to the logical qubit using classical simulations. And so I'm not claiming this is a scalable way to do this like at all, but it does help with the experiment in terms of processing the data in this case. And then the other thing that we do is, we do have some kind of noise or decoherence when we run this experiment, but we want to measure the magic in the pure state. So we're doing full state tomography. So we project the qubit in post-processing into the nearest pure state, assuming that it's probably meant to be in that one. And so this is the experimental data from the IonQ ARIA machine. So we go up to a system size of 16. And so the raw data is what's in this inset here. And then this is when it's scaled according to the system size. And so we do see that it collapses with this root n scaling. And then we also kind of have to adjust the vertical axis, because as we make the system size larger, I mentioned, right, magic is kind of a measure of noise. So we're kind of ending up with more magic than we should have as the system gets larger and larger. So we kind of scale it down based on the system size as well. But we can already see that the peak is behaving as it should in this vanishing code rate case. But this is not the most interesting case, right? So we want to go to an actual finite rate code. So now what we do is we fix, well, we can change the code rate, right? But for right now, let's fix the code rate at 0.5. So we're always going to have half logical qubits and half syndrome qubits. And we'll look at this cut in the phase diagram. And remember this second stabilizer Rainier entropy takes full state tomography, right? And now our system is getting larger and larger. So this is going to become not tractable in the experiment. And so we need to come up with another measure of magic that's going to be actually experimentally realizable. But sorry, so in the numerical case, the theory calculations, we can go ahead and do this up to system size 14. And so we can characterize this, you can see the crossover point here, which has a scaling collapse with the system size. So we have indications already of this phase transition in the magic, and this is the SSRE. So we do this numerically. Okay. So now we're going to introduce a new measure of magic. So this is introduced the first time in this paper, and it's called the basis minimized measurement entropy. And so the kind of wordy definition is that it's the entropy of the Born probability distribution of measurement outcomes. So I take lots and lots of shots, many measurements, and then I look at the distribution of those outcomes that I got, and then I minimize over the set of possible stabilizer measurement bases. So I could measure in the computational basis, or I can measure in the X basis, or I can measure in some other poly string of bases where each qubit is measured in a different poly basis, right? So the idea, let me give you an example to illustrate what this means. So let's say I have the state 0, 0, and I measure in the X basis. I could get 4 equally probable measurement outcomes, and so that has an entropy of 2. However, if I measure in the Z basis, there's of course only one possible outcome, and so that has entropy 0. And so the basis minimized measurement entropy is 0. That's the least entropy that I can have, because I'm able to find a good basis in which to measure that state that minimizes the entropy. Yes, questions? I mean, I guess we're assuming we're measuring like all the qubits at, well, yeah, at once. You mean as opposed to like a Bell measurement or something? Yeah, that's like a totally, yeah, there are magic measures that use Bell type measurements, but that's like a different. In this, I'm assuming we're doing single site. Yeah. You mean like use purity to yes. Purity is not going to be a good measure of magic, though. We need something that's a good measure of magic. You can have a pure stabilizer state. Great. Okay. Any more questions about this measure that we've introduced? Yes.
Can you measure purity? I thought that we were going to get this.
We can talk about it later too. Okay. All right. So what's nice about this is that it avoids full state tomography, right? I'm looking at this distribution of measurement outcomes. And then we take it kind of one step further and look at the conditional entropy, because we're conditioning on the syndrome outcome. And so this sort of tells you the uncertainty about the logical space. And so altogether, we take the basis minimized conditional entropy, where we have this conditioned on the syndrome outcome and then minimized over possible bases. So this is going to be what we, well, not even quite in the experiment, we don't even minimize over possible bases. We just assume that the computational basis is good enough, which of course incurs some errors, but is actually still a pretty good measure of magic. And we'll show why that's true in simulation. But anyway, and then we also add this other error mitigation that's very similar to what you would see in like a cross entropy benchmarking experiment, where we this entropy that we calculate, let's see, one of these is based on classical simulations and the other is the experiment. And so that also gives us another layer of error mitigation. Okay. So now we can first look at some numerics. So this is just looking at the same phase diagram with alpha and R, but instead of looking at the SSRE, we're looking at this conditional entropy. And this is for size n equals 24. So you'll notice these numerics that I present never really go past like 24 qubits. So, you know, in the middle of this phase diagram, we're not doing just Cliffords anymore. So these simulations are actually getting pretty expensive classically already. So without our grad student having to go use the cluster, this is kind of as far as the numerics go. Okay, so let's look at one cut in this phase diagram. This is again numerics up to size 24, and we see you can see this crossover that happens here. That indicates that we've entered into this magical phase, and we have a scaling collapse with n. So this is a phase transition. And we can also observe this in the experiment. And so I would say this is not the prettiest of our data, but we do see some indication of a scaling collapse. But yeah, I think the kind of hit that we take from, yeah, maybe I won't comment on that. Okay, so yeah. Yeah, we're conditioning on the syndrome outcome in order to calculate this entropy. So this is conditioned on this syndrome outcome.
24 is sorry. How many sizes do you do?
Well, so the numerics I'm showing so far are 24, and it's a code rate of 1/2. So we have 12 logical qubits and 12 syndrome qubits. Yeah, so maybe I'll just say that I think that's really one of the big issues with the experiment is just getting enough recurrences of the same syndrome. Yeah, up front, yeah.
This gets the same crossing as other measures?
No, it's a different crossing point because it's a different measure of magic. That's to be expected. Yeah, so I think I said this kind of. Yeah, so we're not measuring, how do I say this? It's not really like a direct magic measure anymore. So the interpretation is a little bit different. Yeah, sorry. This is where it gets into theory land, where I'm like not quite there yet, ready to answer your question. This is my question over here.
First phase diagram, there was a black point to the right of the diagram, but this study.
Yeah, that's what he was asking about. So at the Clifford point, why is this not 0? And I'd have to think about that and get back to you. Yes, it's confusing. I agree. Right. Yeah. Yeah. It's still capturing the phase transition, and so the statement is kind of to say where it's a good measure in the non-magical phase, but it's not such a good measure clearly in the magical phase. And it might just be like a scaling issue that I'm just forgetting. Like somehow this is entropy and not magic, and if you like scale it in the right way, then it would behave. But I don't want to give you an exact answer. Yes. Yeah. So that's why, yeah, we're able to do this experiment at all, because we're not doing full state tomography. We're just looking at this probability distribution of the measurement outcomes. This is going to bother me, and I'm going to have to. I'll try and come back with an answer tomorrow. Okay. So yeah. So we also take one more approximation. So we can take the Rainey approximation of this conditional entropy, which we actually have analytics for. So that's these like solid curves that are on this plot, in addition to the numerics, which is a nice result. I encourage you to read about if you're so theory minded. And so this is showing theory and experiment next to each other. And I think this is the kind of a really nice case where we see this phase transition and a nice scaling collapse that corresponds nicely with the behavior that we expect in theory. So this is on the experiment, we go up to size 16. Yes.
While you're off by like a factor of 2.
Which scaling exponent? Yeah, so there's something that's changing this point from theory to experiment, and I think that's consistent with kind of what we see when we try and measure these kinds of transitions. But I don't have there's nothing like concrete I can say about that. I mean, these sizes are not so different, so I wouldn't say that it's like, oh, it's definitely a size effect. But that probably yes, that probably has something to do with it. Almost certainly does.
So would it be fair to say that your experiment is basically trying to find this boundary? Essentially, like this boundary between the two. Like you're not saying anything past it because, well, depending on which one you take, whether there's even magic.
Right. So yeah. So what we're interested in showing is that there is a measurement induced phase transition in this actually, you know what? Let me come back. My conclusion. I'll say some more. Are there any more questions on the data at this point? Yes, from 0 to pi over 2. Wait, so it's why would you think it's symmetric? Like if we added that in, then it would be, I'm not sure what you're getting at. Yeah. Mm-hmm. Right. So we don't invert the inserted polys. That layer is just a Z rotation.
But isn't that it's symmetric? Can't you just increase alpha? Keep going.
Yeah. I suppose if you went from 0 to pi, it would look symmetric, but that would not be very interesting.
I don't think alpha is part of the group. Alpha is part of the group. One group, two other groups, one group. It's still Clifford.
Yeah, yeah.
It's not like it's-
Oh, you mean like a Z, like a phase flip Z? Yeah, it's a rotation around the Z axis by pi over 2 is the Clifford point. Right, yeah, so you're saying it's equivalent to a phase gate. Or not, maybe. Those aren't the only Cliffords.
It might be the particular location of the phase diagram.
Oh, and I think I did not explicitly say, like, we average over many, many instances of these random Clifford circuits in order to get this data. Sorry, there's some things about like MIPT that I just kind of assumed, like we're always averaging over many, many instances of these circuits. When I say many, many, I mean 50, but it's a lot. It's a lot for us experimentally. And it's enough, right? That's another reason that I think limits the experimental data is kind of our machine time access, right? Only so much patience for this. But any other questions? Yeah. So it's looking at kind of yeah, like on average, when I look at all of these circuits together, is this error that's happening enough to land me in a magical phase and like have magic in my logical state? Or is the decoding step enough to kind of snap back into the, on average, into the stabilizer state? So it's sort of getting at the question of like how much magic needs to happen. Yeah, in a sense. I mean, I think that the more complete picture is to look at this phase diagram.
Jump from 0 to the,
Well,
there one number. No, it's there.
oh, like if it was like completely magical or something like that, or you mean like maximally magical?
In the
Well, what we're calling the magical phase is just on the other side of the phase transition. Well, it's a little bit larger than 0, maybe, and maybe this is yeah, it is larger than 0 a little bit on the other side of the phase transition, but it's a phase transition. It's not like I guess in the thermodynamic limit, maybe it's like a sharp step function, but we can't simulate that. Growing with alpha. Well, so it's kind of getting it maybe like this, right? So it does grow, but then there's this Clifford point here. Yeah. Yeah, so like intuitively, right? Like it should kind of grow and then go back to 0 at the Clifford point, but that there should be a phase transition there with finite size or with this scaling is not clear, like a priori, right?
Maybe this is related to the non-extension, but there's a nice crossing on the left side, but there doesn't seem to be a crossing on the right side.
Over here, you mean? Yeah. So there's the phase transition is here.
Why is there no corresponding phase transition on the right side and go back towards the third direction?
If there's a deep meaning, I don't know it. I'm not sure there is a deep meaning.
I guess what I mean is phase diagram go
Yeah, no, yeah,
Avoid the magic phase, so the phase transition in the
phase transition out. Yeah, that's not accessible in this. I don't know. It's a good question. Okay, running out of time, so let me just kind of say a few things at the end. Okay, so we've started to understand a little bit more about kind of how magic behaves, but there are lots of questions left. So first is that we've made, kind of an attempt at an efficient magic measure that we can access experimentally. As I mentioned, this is only for pure states, so it doesn't include things like decoherence or measurement operations. And there are some magic measures out there that work for non-pure states, but you still need full state tomography. They're difficult to measure. So one question is, can we find more efficient magic measures? And then sort of more generally, I think what is exciting about this result is that we've taken this idea of a measurement-induced phase transition that has been largely studied in the context of entanglement, where entanglement is a resource for quantum computation, and we've shown that there's a phase transition in another resource. And so when you combine this process of when you're creating these, for example, the random circuits, but it could be something else, the Hamiltonian, whatever. You have this process whereby you generate that resource, you do some sort of correlation across the system, so you're creating sort of non-local generation of that resource, and then you do something to destroy it, like measure the syndromes or do these mid-circuit measurements or something like that. So can we take this kind of recipe for an MIPT and apply it to other resources? And then maybe reaching like even further, right? So I mentioned, magic state distillation is a very expensive process. So can we somehow figure out how to do this more efficiently based on our studies of how magic behaves? Okay, so with that, I think I will stop there. Thank you. You can take a few, yeah.
You mentioned you do lots of shots spanned according to what the syndrome results are. So, and then you get a density matrix, and then you project it to the nearest pure state. How do you do that last step?
So for that one, I was talking about the case where we had a single logical qubit. And so we can look at the full state tomography and in the post-processing and basically look for the nearest pure state. So like
that last sort of not trivial.
Yeah, I'm not saying it's a perfect process. So this is also like it's an approximation that happens to help on average. But yeah, I don't want to write it all out right now. Okay. Any other questions? Yes.
Why do you have this encoding and decoding station? Just don't take when
So we're interested in this. How do I say this? I mean, then we wouldn't see anything. So we have to somehow like. So what would, so you're saying just do a random Clifford and measure the magic? Yeah. Yeah, so this decoding process and the syndrome measurement is what kind of does this like snap into a stabilizer state or a magic state. And so I think if you just did, like, I think what you're describing is just a different experiment. So you could do like random Cliffords and insert T gates or something like that, or insert these rotations somewhere else. and people are looking at things like that as well. But it's just a different, we're interested in this in particular in a measurement induced phase transition. So the process of measuring the syndromes is what makes this transition happen. Whereas what you're describing is just a different experiment. Last question.
I guess I'm wondering why it's these two that looked at the magic in the whole state. This undergo transition.
You tell me. Has anyone looked? I don't know. Yeah. So yeah, I guess it's kind of, well, again, a different experiment or different calculation that I'm sure somebody is trying to do right now. But these like I mentioned, right, like we only went up to like 24 in this case, and we had relatively kind of low magic in most of these circuits. There's a reason people like simulating Cliffords, right? It's easy. So when you start doing these like har randoms, essentially, yeah, it's more expensive. So please do it. Yeah. Great. Okay. I think I need to sit down. So I think I'm going to stop there. Thank you.